Greetings, people. This is week 4B. This is the second installment for number theory. Uh, let's see what we've done. The important things we've done so far are, of course, this part right here in particular, defining congruence relations. Okay, when we talk about um, arithmetic with congruences, think of ordinary arithmetic, but with constraints. So it's something you're not used to from normal arithmetic. Okay, and we defined a congruence relationship right here. Do not ever forget this theorem. Okay, the fact that if integers a and b are congruent to modulo m, if and only if there is an integer case such that a equals b plus cam. Okay, which means that if you divide, see, M divides AB. That's basically what this is. M divides AB, and that's what we said here. Okay, if we have integers A and B, if they're congruent modulo M, then there is an integer K such that A equals B plus KM. Okay, so another way of looking at it, conversely, if there's an integer k such that a equals b plus km, then km equals a minus b, and hence m divides a minus b. That is very important, that right there. Okay, hence m divides a minus b, and a is congruent to b modulo m. Those two things are the same. So when you see a is congruent to b modulo m, think of m divides a minus b. If you have a calculation that you need to do, that is what you do. You go straight to that definition. Okay, that's very important. Also, here we have the relationship between the relation, which is a is congruent to b modulo m. Okay, that's a relation. And a more specific kind of relation is a function, and that is a mod mb. That notation, mod, denotes a function. Okay, this thing's a function. This expression is a relation. So this is an equivalence relation. This is a function. Mod is the function. Okay, so make sure you understand those basics. And then we went on to prove a couple of these little babies in here. We went through arithmetic, okay? And the arithmetic here with modulo m, and this was something of a side here, the modulo arithmetic on the subset of m integers, okay? That's what this was. We talked about this. Something you'll see later. I'm not testing you on this, but this is part of the arithmetic of modular, the part of modular arithmetic. So we talked about a few things here about addition and multiplication, as you can see. And then we went on to talk about, we didn't do this part. We talked about multiplication, we talked about addition, but we haven't talked about division, all right? Well, we did actually, we talked about it. Here, this is where we went into this business of the greatest common divisor. We found out eventually that okay, here we use the fundamental theorem of arithmetic. Look for least common multiples as well. Use Euclidean algorithm to do that. This is kind of a very rough overview of what we've done already. And we proved the correctness, which you don't have to do. And then we came up with Bezo's theorem. Now, what is the point of Bezo's theorem? Bezo's theorem is many practical purposes for that theorem, but for us, it's finding inverses. Finding inverses is a little tough. Let's just take a little aside here, okay? Remember that division with modular arithmetic is tricky. You can't always do it. Fractions don't make sense in modular arithmetic. So only some values in division work. In general, it doesn't. So we have to come up with another kind of approach to inverses. So let's just do some preliminary notes. Notes on inverses. So in order arithmetic, we have an inverse times A inverse times A, which gives us unity, okay? So one undoes the other, okay? So for example, now just with arithmetic, we're not doing math, we're not doing calculus. Of course, there are functions that undo other functions. But here we're just simply talking about arithmetic, for example, 1/5 times 5 equals 1. Now that's the problem right here with modular arithmetic. Problem with modular arithmetic is division doesn't always work. So we require an approach to modular inverses that involves the multiplicative inverse. Inverse, okay. The multiplicative inverse, okay. So if we define this way, we say, oops, we say A prime is the inverse. You can also put a bar over it. There's all kinds of ways of indicating the inverse. So we'll just use prime here. Is the inverse of mod A mod M. A mod M. Okay. A prime is the inverse of A mod M. Okay. If multiplying by A yields some sorry about that, expecting an important call. That wasn't it. So let's just keep going here. So we say that A prime is the inverse of A mod M if multiplying by A yields something that behaves like, here we go, 1 mod M. So 1 mod M is kind of like what we'd say is therefore is the multiplicative inverse. A prime times A is congruent to 1 mod M. All right. A. Okay, I hope that looks good. Okay. Where A prime is we got enough room there? Yeah, it's called the multiplicative inverse. i.e. A prime A leaves remainder 1 remainder 1 when divided by M. So I think those are. I think that gives you a lot of, I guess, heads up on this. So let's talk now more about why it acts like an inverse. Question. Oh, for God's sake. Of course, I figured I'd do that. Writing on my own template. Question. Where am I? Have I got it set up right? There we go. Yeah. So question. Why does it act like an inverse? Why? Why this works? Why does this work? Okay. So suppose A prime A is congruent to 1 mod M. Okay. Now multiply both sides. Both sides. By X. Why would I do that? Because I get this result, then A prime times A up X, there you go, is congruent to, that's right, X mod M. Now, I've got an X here, I've got an X here. What's the point of that? It's because I want to show that I have an inverse that goes beyond just the number 1, okay? Just that goes beyond the remainder 1, okay? So I put an X on both sides, and this produces still the same equation, except now it involves a variable. And so this becomes an inverse for all X, and that is why it works. So that to preserve the congruence. For more than 1 mod M. Okay, this right-hand side. Okay. Okay, I mean that's pretty much it. Okay, so multiply by A prime. Say, oh yes, by multiplying by A prime, you get exactly back to where you started. That's the whole point. This brings you back to where you started. Okay, I think that's good enough for inverses. Inverses are extremely important, obviously. You know, in modular arithmetic, you have to be able to go back to where you began. All right, and so let's just get back here. Bezout's theorem helps us do this. Okay, I think we did this already. We did these linear combinations. Consequences of Bezout's theorem is this thing we looked at already as well. We will prove that a prime factorization of positive integers, where the primes are in non-decreasing order, is unique. This part of the fundamental theorem of arithmetic, right? This part of the bad. This is part of the fundamental arithmetic theorem. The other part, which asserts that every positive integer has a prime factorization into primes, will be proved in we need mathematical induction. We looked at this, we did this already, okay? Now here's why we ran into problems, and this is as far as we got. Dividing by congruences by an integer just doesn't work. It can't deal with fractions. It only works in specific cases where you don't have fractions, okay? So now we're finally into this section here, solving congruences. So it's the Chinese remainder theorem. Fermat's little theorem, and I don't think we're going to do these, but we'll have a look. So linear congruence, okay, a congruence of the form AX is congruent to B mod M, so you got a little X right there, is called a linear congruence. So don't forget that. There's congruence and there's linear congruences, okay? Linear clearly because there's just X to the first power, okay? The solutions to a linear congruence, AX is congruent to B mod M, are all X integers X that satisfy the congruence. So definition, integer A, here instead of prime, they use bar, such that A bar times A equals 1 mod M is said to be an inverse of A modulo M. So I gave you the background on it. The book Rosen just throws you into it. And I think you can see there's going to be trouble because it started with dividing. I'm sure the book must talk about this in detail, but these slides his slides omit it completely. The idea of dividing is a problem, and in this form of arithmetic, okay? So here, this, by having an X in front of A, this is called a linear congruence, and here we define the inverse of A and A mod congruent to 1 mod M. So that's the inverse of A mod M, okay? So here, this is A prime times A is congruent to 1 mod M. Right, that's the inverse of A mod M, okay? Makes perfect sense. We're back where we started, you see? So recall the definition of A and B are integers and M is positive. Then A is congruent to B modulo M if M divides A minus B, okay? Don't forget that. So what do we have here? A congruence of the form is linear congruence. We already talked about this. Yes, okay, example 5 is an inverse. If 5 is an inverse of 3 modulo 7, since 3 times 5 is 15, which is congruent to 1 mod 7. Okay, that you can test for yourselves. One method of solving linear congruences makes use of the inverse A bar if it exists. Although we cannot divide both sides of a congruence by A, we can multiply by that. So we've done all that already. We've gone through that, and here's an example of a particular inverse. Okay. Because this takes you to 15 is congruent to 1 mod 7. So that brings you back to where you started. Do you see? That's the whole point of this inverse right here, is to bring you back to where you started, which is A mod M. All right. So inverse, all right. Why inverses are important? Well, we know we've done all this already. See, we've already done this, okay? Instead, you want to find, yes, okay, we've done all this. I guess I put this into the, yeah, okay, I copied this in here. I put my notes into here. So everything I've just talked about is here, all right? So the following theorem guarantees that an inverse of A modulo M exists whenever A and M are relatively prime. That means they're, relatively prime. They both can only be divided by 1. The two integers A and B are relatively prime when the greatest common denominator of A and B is 1. So here in this theorem, if A and M are relatively prime, and M is greater than 1, then an inverse of A modulo M exists. And furthermore, this inverse is unique mod M. This means that there is a unique positive integer A bar less than M that is the inverse of A modulo M. We've gone through this. This is just repeating what we've just done. And every other inverse of A modulo M is congruent to A bar modulo M. And they go through this proof. And that's why the greatest common divisor comes in so quickly and is so underlies so much of basic number theory, and you can see it right here. We can't do this without Bézout's theorem easily, which involves greatest common divisors. So since the greatest common divisor A and M is 1, by theorem 6 of section 4.3, there are integers S and T such that SA plus TM equals 1. I think we did do section 4.3. Let's see here. Yeah, come on. Yeah, this is 4-3 right here. Yeah. Okay. Yes, of course we did. Okay, just want to make sure. So this proof of this theorem has already been proven. Okay. This one here. Okay. This has already been proven. So by that theorem, there are integers s and t such that as plus tm equals 1. Hence, sa plus tm is congruent to 1 modulo m, okay, by definition. Since t times m is congruent to 0 mod m, it follows that sa is congruent to 1 mod m. Consequently, s is an inverse of a modulo m. And exercise 7 proves the uniqueness. This is just simply how you prove theorem 1 right here. Theorem 1 is if a and m are relatively prime, and then an inverse of a modulo m exists. Okay, so the requisite is relative primality. All right, that's the takeaway from this. In order to find an inverse, you need to have um, um, relatively prime integers such that a modulo m exists. Okay, all right. A and m are relatively prime. Okay, that's pretty straightforward. Finding inverses. So let's see. What do we have here? Okay. All right. So we want to find an inverse. Find exercise. Find an inverse of 3 modulo 7, of 3 mod 7, modulo 7. Solution. Using the Euclidean algorithm, 7 equals 2 times 3 plus 1. All right. 7 equals 2 times 3, 6 plus 1. Okay, so that is from the Euclidean algorithm. You just accept that for now. You can do it. It's trivial to do. From this equation, we get minus 2 times 3 plus 1 times 7 is equal to 1. 6 plus, that's negative 6, negative 7. Yes. Or minus 7 equals 1. Okay. 2 times 3 is 6 plus 1. Okay. That's minus 7 times 7. Okay, good. Okay. So see that minus 2 and 1 are Bezout's coefficients. Remember we talked about those? Bezout's. How do you spell him? All right. Bezout's coefficients. That was discussed just yesterday, just shortly by before the end of the presentation. Right. Hence, minus 2, as you already probably figured, is an inverse of 3 3 modulo 7. Okay. Also, we can say every integer congruent to minus 2 modulo 7 is an inverse of 3 modulo 7. That is, i.e., 5 minus 9, 12. So there's that pattern, okay? There's that pattern, and that's why we place the x in that derivation of the inverse that we did just before this slide. We went back to the presentation. So that generalizes it so that it's not just for 1 modulo m, it's for x modulo m. So you get these patterns, okay? That's what modular arithmetic is all about. It's about cyclic patterns. Don't forget that. Unlike ordinary arithmetic, modular arithmetic is about cyclic patterns. Yes, okay. So that's that. It's pretty straightforward. Make sure you understand that. So find an inverse of 101 modulo 4620. That's different. Now we have to do this. Okay, we have to do the Euclidean algorithm where we get down to, since the last non-zero remainder is 1, that's what we're looking for. GCD 1014260 is 1. Okay, Bezout's coefficients, therefore, are minus 35 and 1601. Okay. So, as you can see right here, minus 35 and 42, minus 35 and 1601. Okay, so we can work backwards. We go from here and do the same thing, but this is backward substitution, and we end up, with this final result that 1601 is an inverse of 101 modulo 42620. All this is a more complicated example, a real world example where here the Euclidean algorithm is trivial. We're using it for these small numbers, but for bigger ones, all this is doing is it's going through the same thing. You go through this process, you get the inverse, and then you get Bezout's coefficients. And that's what we're doing here. And so these are Bezout's coefficients. And from this backwards analysis, inverse substitution, using the inverse, you find, using Bezout's coefficients, you end up with 1601 and 101, 1601 being the inverse of 101 modulo 42620. Okay. That's a mistake. This is obviously a mistake. All right. Okay. This should be, that 2 shouldn't be there. So it's 4620. That's a mistake. All right. Make a note of that. And this is clearly a mistake. That's what threw me off looking at that. I was trying to figure out where they got that from. But you can see up here, that's what we're looking for. Okay. Using inverses to solve congruences. Okay, so we can solve a congruence. Here's a linear congruence. Okay, x is congruent to b mod m by multiplying both sides by this inverse. So example, what are the solutions of this congruence? 3x is congruent to 4 modulo 7. Let's just walk through it, okay? And instead of writing through, this is mostly writing, so I only like to write out the stuff with the math. So we found that minus 2 is an inverse of 3 modulo 7. And 2 slides back. Now we multiply both sides of the congruence by minus 2, obviously. Here's the congruence, and we want to find the inverse. So that's actually apply the inverse to solve the congruence. It's kind of like, you've got x squared, that's the operation going forwards, and the inverse operation, of course, is the square root of x squared, which brings you back to where you started with x, okay? Before you squared it and took the square root of it, okay? So because minus 6 is equal to 1 mod 7 and minus 8 is equal to 6 mod 7, it follows that x is a solution, okay? Then x is equal to minus 6 mod 6 modulo 6 mod 7, okay? Again, just going back to this linear, we haven't shown yet how to solve linear congruences, and here we use inverses to actually solve for x, if you can see. So we need to determine if every x with x is congruent to 6 mod 7 is a solution, all right? Assume that x is congruent to 6 mod 7, then by theorem 5, oh God, wherever the hell it is. Okay, forget it. There's no sense in moving back, wasting time. In 4.1, way at the beginning, it follows that 3 times x is congruent to 3. 6 equals 18 is congruent to 4 mod 7, which shows that all such x satisfy the congruence. Okay, so we're satisfying all of these various values of x for the solution to this linear congruence. So the solutions are the integers x such that x is congruent to 6 mod 7, namely, here you can see how it is. It's got to be 6, and then 13, and then 20, and all the way to minus 1, minus 8. So this thing cycles in units of, in patterns of 7, okay? 7, okay, get away. And so those are the solutions to this linear congruence. I'm having a tough time talking today, stuttering. Oh, now what? Why is this not working? Fine. And so now finally we hit the big one. Okay, this is the most important theorem of this section, the Chinese remainder theorem. Okay, and this goes back to Sun Tzu. Don't laugh too hard at me. Okay. Who is this? The same guy that wrote The Art of War? Well, I'm not sure. There are certain things whose number is unknown. Oh, that's interesting. When divided by 3, the remainder is 2. When divided by 5, the remainder is 3. So we're looking for the pattern here. When divided by 7, the remainder is 2. What will be the number of things? Okay, so start again. When there are certain things whose number is unknown. So when divided by 3, the remainder is 2. When divided by 5, the remainder is 3. When divided by 7, the remainder is 2. This is a pattern that we can solve. There it is right there. It's these things. Okay, the Chinese remainder theorem allows us to solve systems of linear congruences. The Chinese remainder theorem allows us to solve for x in a system of linear congruences. Okay, this is a system, not just one, it's a system. The puzzle can be translated into the solution of the system of congruences, blah, blah, blah. We'll show how the theorem that is known as the Chinese remainder theorem can be used to solve Sun Tzu's problem. Okay. Theorem 2, Chinese remainder theorem. Let M1 all the way to Mn be pairwise relatively prime positive integers greater than 1. Pairwise relatively prime. And A1 through AN be arbitrary integers. Then the system x congruent to A1 mod M1 all the way down to x congruent to AN mod N has a unique solution modulo M equals M1 times M2 all the way times Mn. That is, there is a solution x with x between 0 inclusive and M exclusive. And all the solutions are congruent modulo M to this solution, okay? So you are supposed to look at exercise 30 for the proof. Chinese remainder theorem is extremely important. Make sure you know how to prove it, okay? It's simple enough to understand. It's just we've already gone through what solutions to linear congruences are. Now we're looking at systems of linear congruences, and so we'll just construct a solution first that this big M sub k be m over m sub k for all the n integers, and m equals m1 times m2 all the way to mn. Okay, let that exist. So since the greatest common denominator of m sub k and big M sub k is equal to 1, by theorem 1, there is an integer y sub k, which is an inverse of m sub k modulo little m sub k, such that big M sub k times this integer, yk, an inverse, is congruent to 1 modulo mk. So you can see this is just the same thing we already did, but involving systems of linear congruences now. So it's nothing new. It's exactly the same. If you understood the solution of linear congruences, then systems of linear congruences is just simply indexed like this. Form the sum x is a1 times big M1 times y1. There's an integer y sub k, an inverse. I'm telling you, man, Rosen just doesn't know good grammar. I wish I could fix these slides, but these are impossible to edit. Okay, all terms. Note that because big M sub j is congruent to 0 mod m, whenever j is not equal to k, all terms except the kth term in the sum are congruent to 0 mod m sub k, little m. Because big M sub k times y sub k, the inverse, is congruent to y modulo little m sub k, we see that x is congruent to a sub k times m sub k times inverse y sub k, which is congruent to a sub k mod m sub k. This is just for systems, for k being 1, 2, all the way to n. Okay, this is just for solving for systems of linear congruences. Hence, x is simultaneous a solution to all of these congruences, like all these ones here. So consider the 3 congruences from Sun Tzu's problem. When we just looked at those when we first started looking. X is congruent to 2 mod 3, x is congruent to 3 mod 5, and congruent to 2 mod 7. So let m, little m, like according to the algorithm, be 3 times 5 times 7, and which equals 105. And let big M1 be m over 3, which is 35. Big M3 equals m over 5, which is 21, and big M3 equals m over 7. See, it's 3, 5, and 7, which is 15. So we see that 2 is an inverse of M1, which equals 35 modulo 3, since 35 times 2 is congruent to 2 times 2, which is congruent to 1 mod 3. Okay? 35 times 2. I said 2, yes. 35 times 2, that's the result right here, times 2 is congruent to 4 modulo, congruent to modulo 1 mod 3. And the same for 1 with M2, and 1 is an inverse for M3. So according to the Chinese remainder theorem that we've just seen here, how we sort things together, it's a very simple algorithm. X is a sub 1 times m sub 1 times y sub 1 plus a sub 2 times m sub 2 times y sub 2, and with the 3's. And when you substitute all the values, you get that 233 is congruent to 23 mod 105. So we have shown that 23 is the smallest positive integer that is a simultaneous solution. So there is at least one value of x, the smallest one, that solves this system. Please understand this. And I beseech you at this point, let's see, back substitution. I want you to, we can also solve systems of linear congruences with pairwise relativity prime moduli by rewriting a congruence as an equality using theorem 4 in section 4.1. Substituting the value for the variable into another congruence. Okay, this is back substitution. This is something you'll get used to later on. It's just the inverse process of achieving the same thing. Continuing the process until we have worked through all the congruences, this method is known as back substitution. So example, use the method of back substitution to find all integers x such that x is congruent to 1 mod eb, x is congruent to 2 mod 6, x is congruent to 3 mod 7, following this algorithm. So you do that. I think you can do that on your own. Let's see. Yeah. Well, I guess I could write this out for you. Let's do that. Yeah, let's find a paper. So let's have a look at that. So here, all right, back substitution. Okay, that seems to be there, yeah. Okay, example. Use BS to find all integer. I've got to copy this. To find all integers x such that x is congruent to 1. X is congruent to 1 mod 5. All right. X is congruent to 2 mod 6. And x is congruent to 3 mod 7. Okay. So that's the example solution. Substituting into the second congruence, yields 5t plus 1 is congruent to 2 modulo 6. Okay. Solving this implies t, which equals to 6u plus 5, where u is an integer. So u is an integer, okay. From theorem 4, from chapter 1, again, t equals 6u plus 5. We're using, I just wrote that down. God almighty. Yeah, I'm rewriting. Wait a minute. Term 4 equals 6u plus 5, where u is an integer. All right, I'm getting lost here. I'm sorry. What do I do here? Okay, solving this. Okay, substituting back. Okay, that's what I'm doing. Substituting back into x equals 5t plus 1 yields x equals 5 times 6u plus 5, all right, which is congruent to 3 mod 7. Okay. By theorem 4 again, u equals 7v plus 6. Yeah. Where v, again, is an integer. All right, so this is the last substitution. So substituting this for u into x is equals 30u plus 26, okay, tells us, you see that? Yeah. That x is congruent to 30 times 7v plus 6. There. Okay. Plus 26. Not, okay. X equals, not congruent to, what am I talking about? Jesus. Equals, there's no congruence here. It just equals that set of coefficients, all right? Which equals 210u plus 206, all right? So, thus, x equals 206 mod 210. So that's moving backwards. That's moving backwards. You got that? I hope you do. And yes, that finishes that chapter, okay? That finishes that chapter summary of solving congruences. Okay, here's a 10-point outline. Say points 1 through 6 show how to solve a single congruence, generalized to multiple congruences, and then verification of the solutions against the original. So that's what back substitution does. So that's what we're doing here. Never mind what point 6, and that's something from Rosen that I didn't include. Summary of solving systems. So what congruent to modulo n actually means, core idea is A is congruent to B modulo n means n divides A minus B. Okay, turning the equation into divides, well, it's just by doing this. Don't forget this. Don't forget this. There's your linear equation. And by the definition of modular arithmetic, you have AX minus B now instead of just A minus B. So this removes the mystery. It's just integers. So that's the algorithm to first obtain inverses and then be able to solve these systems of linear congruences. Okay. Then there's this is just more summary, of what we've just gone through. What the coprime means. Okay, so this is summarizing this particular section, 4.5. What does it mean? How do we end up with dividing? And we do multiplicative inverse. How do we know the GCD exists? So there's a test for that. So it's either D doesn't divide B. That's no solutions. D divide B's. Solutions exist. Decide if solutions exist at all. So that's some congruences are impossible. And coprime coefficient. Okay, this is the turning point. This is the moment where multiplication becomes reversible. Cancellation becomes legal. Inverses exist. So that was the turning point where we started deriving a multiplicative inverse. And then, we described how we could come up with a multiplicative inverse. I think I'm going to take all these slides out there. They need a little more clarity. Interpret solutions as sets. Each congruence restricts X to a set of integers. So for example, we got that system and China's remainder theorem. Well, what is it? When do multiple congruences have a common solution? How often do those solutions repeat? Conceptually, each congruence is a filter on the integers. Yes, the Chinese remainder theorem describes when the filters overlap. If the moduli are coprime, the overlap exists, and unique modulo is the product of the again, I just don't know what this is saying. So it is a new technique. It is guaranteed that the combination step works. So you got to know the Chinese remainder theorem. I've just forget these. Just forget this. We just did something like this. You go through this example yourself. This is really good. It's a step by step. It goes exactly. It's a different one altogether. Make sure you can do this. Make sure you understand this. I mean, this is the kind of thing that is supposed to be an exercise for you to be able to just do it on your own. Make sure you do these 4-step problems. What's that? 4, 5 is back substitution, and then you solve, and then back substitute to find x and the final solution. So this is an excellent exercise. Okay, this solving this a set of 3 linear equations, congruences, is absolutely essential that you practice and know this. This will be on the midterm, I assure you. Okay, and that's a different example. Okay, we're finished now with this. Well, I want to show you something else now, if I may. All right, this is an example. This is an example of something that appears here. Okay, I sent you this. Okay, can you see that? I hope you can. Let's see. Yeah, no. There. No. There it is. You can see that. Okay. So this is a paper that I included. You can see right here where it fits in. So it's just right after modular number theory. And then there's these other things that I have, divisibility and congruences. I haven't posted that. But here, Chinese remainder theorem, that's posted on our website. Know how to do these examples. And there's a good one right there. Does that look familiar? Okay, that looks a little bit familiar using the Chinese remainder theorem. Here, look at this one. Really familiar based on what I just showed you. So this is a good set of working examples that will prepare you for the meat of Chapter 4 that you'll be tested on the midterm. The midterm being just 2 weeks away. Okay, we're in week 4 right now. It's week 6. That's when we get to meet each other and room AQ3181 face to face for the first time. Isn't that going to be delightful? So, yes, I could show you more. I could go through a little bit more, but again, I want to cut it short just in case this stops recording within an hour and a half or so. I'm not sure where it is, but sometimes it just truncates. Okay, that's it for now. I might pop in on the weekend and give you some more solved examples just for fun. Okay. Other than that, cheers for now. Okay, bye-bye.